Hey guys, how's it going? So last week we managed to calibrate our robot and find the stop values. This means this week we can now use these to write and have our robot go for an initial drive. The worksheet does say we should write reusable functions, so I'm going to hand you over to Mr. Ariel.
Hey guys, so today we're going to be creating two functions for the driving part. One to move ourselves forwards and backwards, and the other to rotate on our axis. So we see that in addition to this, we also are going to be using the switches maybe to tell the robot to start, for instance. We'll go back to that a bit later. Because down here we see that the two functions they want us to create is indeed move straight and turn angle. And this will allow us to, in the end, for instance, make the robot drive in the shape of a letter.
Okay, so I'm guessing the first thing we need to understand is what our goals are. When I looked at the worksheet, I had a bit of confusion trying understanding what they are, but I remember someone told me the best way to do this is you break it up by first writing it out as comments in English. Would you say that's correct, Mr. Ariel?
That's a perfect approach to take in this case. So we can just jump down into editor and you see that we have some what I like to call boilerplate code here. Much of that is the same as what we sort of ended up with last time, just when it comes to how we have set up our servos, our left and right servo, and we have attached these servos with our shorthands here. And also we've, now that we have the midpoint values for our servos, we've actually told the servos to sort of assume that speed, and that speed of course is 0.
So over there I see servo L mid. Essentially you mean that's the midpoint value which we've redefined at the top above there, if you just highlight that.
Exactly. So what you see up here is that we've created a new define here, and that basically says that servo L for left, mid, should be equal to 82. So 82 is what I found for this robot that we're using now, is the value you need to write to the left servo for it to stand perfectly still.
That all makes perfect sense. The only new thing I see there is cosmological constants depending on friction and battery level.
Indeed.
Could you please explain those, sir?
Yeah, so these are basically just numbers that I found by trial and error for this particular robot.
Okay.
And it just tells us how long the motors have to be engaged in order for the robot to travel, in this case, 1 centimeter. Or in this case, to rotate 1 degree. So we see that hey, in this case, we need to leave the motors on in the forwards direction or backwards direction for 140 milliseconds for the robot to travel 1 centimeter.
Okay, I mean, I think I understand it, but for the purposes of clarity, to really nail this down, let's switch over to the other screen and give a quick demo.
Sure. So what you need to do is to have the robot drive straight ahead for a given time interval, and I've chosen 2 seconds here, and we see that it's traveled 16 centimeters. So 16 centimeters over 2 seconds. If we want to see how long it takes to drive 1 centimeter, we need to divide this by 16, right? 2 seconds divided by 16 is equal to 125 milliseconds. So we see that the robot is actually a bit faster now compared to the numbers we are operating with, simply because I've just changed the batteries.
Now that we've got that nailed down, the rest is simple. Left servo, right servo, 0 begin. Okay, I get where we are. Let's get started. Let's carry on.
Okay, so back to what we were talking about earlier. We want to sort of get an overview, right? We have some goals we need to cover. So let's start with the switches. Let's say that we have the switch make the robot go. That's vague enough for us. And also we had to write
a function.
Let's just say write functions to drive robot. So the last one, and maybe the main goal, is to draw a letter. So
the method you're using now, I found it very helpful, in fact, where we first write the notes to understand it in English first before we write any line of code, because it's so easy to confuse yourself writing lines and lines of code and think, where am I, what am I doing again?
Yeah.
It takes the magic out.
I think, I mean, this is a really trivial list, but it outlines what we have to do. So we don't necessarily have to attack this chronologically, though. We could just start with the functions to drive the robot. If not, the letter isn't going to be drawn anyway. So let's start with the functions.
Makes sense.
So we start by saying that we have a function called move straight, and it should take a distance, right? So let's say that it should take, for now, just call it an integer, and for X amount of centimeters, it should move straight. And so what it really should do is it should activate the motors. It should wait until we've traveled that amount of centimeters, and then it should stop the motors. And one thing I want to sort of point out here straight away is that we have another function that's going to be doing something really similar, and it too will need to start and stop the motors.
Okay.
And so if we sort of take a look at what that means that we have to say left servo dot right, and then draw upon the shorthand, right? We see that we have do servo left forward. That is our shorthand for saying that the replace that with whatever number that sort of
Shorthand being what I referred to as nicknames in the previous chat.
Nicknames, labels, shorthands, defines, many
Same thing, yeah.
many ways to say it. But anyway, so we see that for the left one and the right one, they are the way they are laid out on the board means that we have to make one go counterclockwise and one go clockwise for the robot to move straight. And so this is just again to keep our sort of tongue straight and help with that. So anyway, for this function, we would then have to say left servo forwards, and then right servo R forwards, and then we would have to now we've done that, so we have to wait, and that would just take the form of a delay. And this is when the relationship between time and displacement comes in handy, right?
Yeah.
Because we want to wait for something that's proportional to the amount of centimeters that we are traveling.
Yes.
So centimeters, for instance, 1 or 10, and we would times that with
Servo milliseconds?
Yes. Servo milliseconds per centimeter.
Yeah.
And this, of course, is because the delay function takes a milliseconds as an argument. So if we were to travel 1 centimeter, this would equate to 140. If we were to travel 10 centimeters, this would have to wait for 1,400 milliseconds, or 1.4 seconds.
And so how do we stop them? We stop them by writing the stop values, is that correct?
Yeah, the midpoints that we found earlier would make the the robot stop. So indeed.
Okay.
There we are. So this function is now effectively done.
It makes
really.
sense. I've got a question. Is there not a cleaner way to do that by writing one function, as we did in the previous task?
Exactly. So the thing here, right, is that if we now go on and say, okay, let's do the turn angle function, what we find is that we have to sort of repeat ourselves quite a bit. And maybe there's a better way of doing that, but I see you pointed out. I certainly would sort of feel inclined to now instead write a function that is called set speed, maybe.
Yeah.
Because that would allow us to take in just the speed for the
Servo in general.
Yeah. Left speed and write speed, and then basically just put this stuff in here. So now we suddenly have a function that sort of takes one line instead of two, and is also more general, right? The move straight function doesn't need to know about the servo objects and all that jazz. It just needs to sort of know that it can set a speed for both servos.
Yep, so far making sense, yep.
You would then say set speed and servo L forwards and servo R forwards. And similarly, the same would happen down here. Set speed servo L mid and servo R mid. So we replaced it, and the sort of gains aren't immediately obvious here, but now that we write our turn angle function, it will become a bit more clear. So this takes an angle, and if angle is greater than 0, then we should turn one direction.
Okay.
And if not, then in this case, angle is less than 0. To be perfectly honest, it's less than or equal to 0. That edge case of 0 really isn't something we'll be covering. Of course, for your assignments and stuff like that, defensive coding would sort of dictate that we should guard ourselves against this edge case. Okay. But for now, let's just leave it be. It's not really what this is about. So if the angle is positive, then we should turn counterclockwise, and so the left one then should really be turning backwards, and the right servo should be turning forwards.
Yeah.
Right? And if the and if we were turning clockwise, the reverse would apply, right? And this is when we, of course, have to delay, and we get to use the relationship number that we found above. So we delay for angle times servo ms per degree.
Per degree, that's the one. Okay.
So, of course, after that, after we're done, we set the speed to the motor's resting speed. So just copy and paste that from above.
Yep.
It's the same. And now we have two functions that allow us to move straight and turn at an angle. So one thing, actually, before I forget, we see that angle can be negative. And what happens if we try and delay by a negative number? That's not good. So actually, it turns out that Arduino's got a handy little function for us here to use. We can use the absolute value of angle.
Okay, can we
Right,
just
so-
run through that one quickly? You said Arduino has it. Is that within the Arduino library itself?
Indeed. So Arduino's got a bunch of helper functions, right? Like digital write, digital read, analog write and read, and also functions like abs for the absolute value.
Okay.
It's just really helpful little functions that make our lives a lot easier.
Okay.
So now we ensure that angle will always sort of be in this expression right here will always be a positive number.
Yeah.
Or 0 again. And so we've effectively done this now. This is okay.
Okay, this seems to all make sense. I remember Switchers did it in the previous video. Before our code gets too complex and too large, I'm guessing it's a good point to test it.
Absolutely. So actually our main goal is drawing a letter, and in a way testing this means driving, and drawing a letter means driving. So let's just draw a simple letter, shall we?
Let's do that.
So maybe V is a good starting point. It's basically 2 lines with a rotational offset, if you will. And
so to do this, I'm guessing we call in our function, which is by starting, which we call move straight, is it?
move straight.
And move straight then calls in, alright, that function.
Yeah, so let's just move straight for 20 centimeters and turn for 150 degrees maybe before
Good
we...
place to stop.
Yeah.
And I'm guessing these are just trial and error for the turn angle, is it?
Absolutely.
Okay.
At this point, we're just writing in some numbers that seem reasonable. And you'll find that a lot of this is, when you're testing, you have to sort of just start somewhere.
Okay.
So after we've turned, we need to move straight. Of course, we could now maybe implement and facilitate driving backwards in the same manner that we allowed negative values for the angle to mean turn at a different angle. Maybe negative centimeters could mean move backwards. So instead of turning 150 degrees, we could turn 45 degrees or something like that.
Okay.
But for now, let's keep it simple. Let's say that we move back up again the other leg of the V, and this should be pretty much it.
Okay.
And maybe now, just to make sure that we agree that this is done, say delay, and just make it stand still for a second before it repeats itself, seeing as we are in the loop here. Okay, so I'm just gonna compile this now, and of course we made an error. It should be set, and let's just check that things are actually the way they're supposed to be, and this doesn't look good. It should, of course, it's supposed to be
Right.
It's supposed to be the
Right speed, isn't it?
right speed, indeed. Don't want to write the same speed to both servers. That would make it just turn in a circle all day long. So now, hopefully, this will compile, and that allows us to take it out for a test drive.
I must say, that wasn't a bad V at all. Sorry for doubting it. Shall we jump to the buttons then? And this is pretty simple. It's all we're doing is we're adding button control, and we did this in the last exercise, if I'm not mistaken. So let's just jump in and write that code.
Yeah, so all we want to do here is, instead of this sort of just doing this forever and ever, maybe we should have it do it after we press a button instead, right? So let's remove these lines here now and think about how we could implement this. So I would just have it loop and do nothing while the button is not pressed.
Okay.
So that the second we press the button, the loop condition becomes false, and we jump out of the loop and essentially, or rather, we jump out of the while loop and sort of continue execution. And let's just sketch this up here. While digital read and
Just low.
button
2 or 1.
let's say button 1. While button 1 digital read equals high when it's not pressed, right?
Yeah.
Remember, this is activated or pressed when it's low, or rather it's low when it's pressed. Kind of weird button there. When that is high, just do nothing, I guess. Just wait about. And so we see that when the button is not pressed, it's just going to endlessly loop inside here.
Yeah.
And the second we press the button, it's going to move on down to performing its awesome little dance move here.
Okay.
And then when that's done, it goes back up to the top. The loop function is called again, and while the button is not pressed, it's gonna wait there again and rinse and repeat. And voila, that last part is really
very simple.
Yeah, rather
all
simple.
right, for the purpose of clarity, I think I'm going to summarize this again. So right from the very top, we started by including the servo library, which is include servo H at the top, and as I can see, you've put comments there, which are helping us make it easier to read.
Yep.
And as seen on the comments, defined the pins as button 1, button 2, left servo, right servo. Servo direction, right? This is the value we got from the calibration, the previous task.
These specifically, yeah?
These
the
specifically
midpoints we found.
For this specific Arduino.
And through trial and error, we found that for the left servo to move the robot forward, we have to write 180, and for it to move it backwards, 0, and the reverse for the right servo, right?
And then for moving on to the cosmological constants, depending on the friction and battery level.
Yes.
These are the figures that we need for how long the distance is and the turn angle. And then we've got left servo, right servo, which come from the library. And here is where our first functions come in. The functions are first we attach, obviously.
Yeah, naturally. I mean, in this setup, we do all the boilerplate, the regular stuff. We attach them and we make the servo sort of
and then write
stop.
the midpoints, and we've got it stopped.
All that jazz.
And then write down the while, which essentially is the button, where we're telling it whilst the button is not pressed, do nothing.
Yes.
And then once the button is pressed, we start calling in the functions we wrote down below. And the first function is move straight.
Yep.
The second one is simply turn angle and move straight again. A little bit further down are our functions, which by now I hope we all know I know how functions are done now. It's quite logical. We're defining it to move straight, integer of number of centimeters, and we've written that all down by setting the speed, delay, calling in the left servo midpoint, right servo midpoint. It's all self-explanatory. Turn angle, pretty much the same. If you could explain turn angle for Mr. Ariel again, that would be great.
Yeah, so the turn angle function is a bit more advanced than the move straight because it allows us to either turn clockwise or counterclockwise.
Yeah.
Right, so what we see is that we allow both a negative and a positive value for the angle. And if we follow sort of the standard for mathematical notation, if the angle is positive, then it's counterclockwise. So we could add in a little comment here going counterclockwise. And we see that from what we set the speed to from the servos. If the left servo is propelling us backwards and the right servo is propelling us forwards, we are turning towards the left.
Yeah.
And in a counterclockwise manner. And then if the angle is below 0, or if the edge case is hit here, then we'll turn clockwise instead. So effectively, we could then go up here and say, turn the other direction.
Makes perfect sense.
Right, so now the V is simply going to be in a different angle from the initial leg.
I understand. And then there I see the next thing we do is we then delay, and we delay using an abstract, which is part of the Arduino library.
An absolute.
Absolute,
Yeah.
that's what I mean.
That's just
Absolute.
a sort of a helper function to get the absolute value of the angle, since it could be negative. We don't want to multiply by a negative number here for the delay.
I understand. And then we set the speed for the left and the right, and that's that one done. And the last one is a simple little helper function we wrote, which we found easier to have us write one line instead of two. So rather than writing left speed, right speed all the time, we just did it once over here and we call it further back. Is that correct?
Indeed. So yeah, this is just a little one of these helper functions that you inevitably end up writing. And yeah, it just makes it a bit more readable up here, right? Set speed. We don't have to concern ourselves too much about these objects.
Perfect. Makes sense. I think we're done with this worksheet, aren't we?
Yeah, pretty much. By all means, what you'll find is that if you enter in a negative number for the centimeters to the move straight function, it's gonna do funky stuff.
Yeah.
Right? And there are lots of, as we discussed down here, there is an edge case if you put in the angle if you put in 0 for the angle,
yeah.
then it's gonna really just rotate to the right. Well, actually, it's not gonna even do that. It's just gonna sort of start and stop again. But these are edge cases that we won't go into them too much in these tutorials. And the reason for that is simply that there are tons of different ways of doing stuff. And for instance, what you see here is that we just say every argument here is just going to be an integer unless there's a need for it to be otherwise. But in reality, we're rarely going to be traveling more than a couple of tens of centimeters. So this could instead maybe be a byte to conserve a bit of RAM, right?
I understand. And just to clarify for the last time, this isn't the only way to do this. There are many ways of implementing this. This is just how we decided to do it for this exercise.
Indeed. So hope you've learned some from that, and be sure to leave any questions or comments down below.
Thank you. Laters. Bye.